All right, let's see how much chemistry I can read tonight. It's Saturday. I got nothing else to do. Let's do some chemistry. Let's do at least one chapter now, and then maybe one section of the Bible. And then if I'm still feeling like reading, then I will, I guess, add on to that. But till then, I kind of want to just do some chemistry and some Bible tonight. All right, chemistry, chapter 7, chemical bonding and molecular geometry. Chapter outline: ionic bonding, covalent bonding, Lewis symbols and structures, formal charges and resonance, strengths of ionic and covalent bonds, molecular structure and polarity. Introduction. It has long been known that pure carbon occurs in different forms, allotropes, including graphite and diamonds. But it was not until 1985 that a new form of carbon was recognized, Buckminster fullerene. This molecule was named after the architect and inventor R. Buckminster Fuller, whose signature architectural design was a geodesic dome characterized by a lattice shell structure supporting a spherical surface. Experimental evidence reveals the formula C60, and then scientists determined how 60 carbon atoms could form one symmetric stable molecule. They were guided by bonding theory, the topic of this chapter, which explains how individual atoms connect to form more complex structures. 7.1 Ionic bonding. By the end of this section, you will be able to explain the formation of cations, anions, and ionic compounds, predict the charge of common metallic and nonmetallic elements, and write their electron configurations. As you have learned, ions are atoms or molecules bearing an electrical charge. A cation forms when a neutral atom loses one or more electrons from its valence shell, and an anion forms when a neutral atom gains one or more electrons in its valence shell. Compounds composed of ions are called ionic compounds, or salts, and their constituent ions are held together by ionic bonds. Electrostatic forces of attraction between oppositely charged cations and anions. The properties of ionic compounds shed some light on the nature of ionic bonds. Ionic solids exhibit a crystalline structure and tend to be rigid and brittle. Excuse me. They also tend to have a high melting and boiling points, which suggests that ionic bonds are very strong. Ionic solids are also very poor conductors of electricity for the same reason. The strength of ionic bonds prevents ions from moving freely in the solid state. Most ionic solids, however, dissolve readily in water. Once dissolved or melted, ionic compounds are excellent conductors of electricity and heat because the ions can move about freely. Neutral atoms and their associated ions have very different physical and chemical properties. Sodium atoms form sodium metal, a soft, silvery white metal that burns vigorously in air and reacts explosively with water. Chlorine atoms form chlorine gas, Cl2, a yellow-green gas that is extremely corrosive to most metals and very poisonous to animals and plants. The vigorous reaction between the elements sodium and chlorine, forms the white crystalline compound sodium chloride, common table salt, excuse me, which contains sodium cations and chloride anions. The compound composed of these ions exhibits properties entirely different from the properties of the elements sodium and chlorine. Chlorine is poisonous, but sodium chloride is essential to life. Sodium atoms react vigorously with water, but sodium chloride simply dissolves in water. The formation of ionic compounds. Binary ionic compounds are composed of just two elements, a metal, which forms the cations, and a nonmetal, which forms the anions. For example, NaCl is a binary ionic compound. We can think about the formation of such compounds in terms of the periodic properties of the elements. Many metallic elements have relatively low ionization potentials and lose electrons easily. These elements lie to the left in a period or near the bottom of a group on the periodic table. Nonmetal atoms have relatively high electron affinities and thus readily gain electrons lost by metal atoms, thereby filling their valence shells. Nonmetallic elements are found in the upper right corner of the periodic table. As all substances must be electrically neutral, the total number of positive charges on the cations of an ionic compound must equal the total number of negative charges on its anions. The formula of an ionic compound represents the simplest ratio of the numbers of ions necessary to give identical numbers of positive and negative charges. For example, the formula for aluminum oxide indicates that this compound contains 2 aluminum cations for every 3 oxide anions. It is important to note, however, that the formula for an ionic compound does not represent the physical arrangement of its ions. It is incorrect to refer to a sodium chloride molecule because there is not a single ionic bond per se between any specific pair of sodium and chloride ions. The attractive forces between ions are isotropic, the same in all directions, meaning that any particular ion is equally attracted to all the nearby ions of the opposite charge. This results in the ions arranging themselves into a tightly bound three-dimensional lattice structure. Sodium chloride, for example, consists of a regular arrangement of equal numbers of sodium cations and chloride anions. The strong electrostatic attraction between sodium and chloride ions holds them tightly together in solid sodium chloride. It requires 769 kilojoules of energy to dissociate 1 mole of solid NaCl into separate gaseous sodium and chloride ions. The electronic structures of cations. One sec. When forming a cation, an atom of a main group element tends to lose all of its valence electrons, thus assuming the electronic structure of the noble gas that precedes it in the periodic table. For groups 1, the alkali metals, and 2, the alkaline earth metals, the group numbers are equal to the numbers of valence shell electrons and, consequently, to the charges of the cations formed from the atoms of these elements when all valence shell electrons are removed. For example, calcium is a group 2 element whose neutral atoms have 20 electrons and ground state electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. When a calcium atom loses both of its valence electrons, the result is a cation with 18 electrons, a plus 2 charge, and an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. The calcium ion is therefore isoelectronic with the noble gas argon. For groups 13 to 17, the group's numbers exceed the number of valence electrons by 10, accounting for the possibility of full D subshells in atoms of elements in fourth and greater periods. Thus, for a charge of cation formed by the loss of all valence electrons is equal to the group number minus 10. For example, aluminum forms 3 plus ions. Exceptions to the expected behavior involve elements toward the bottom of the groups. In addition to the expected ions, I think that's tantalum, thallium, tin, lead, and bismuth. A partial loss of these atoms' valence shell electrons can also lead to their formation of those ones. The formation of these plus 1, plus 2, and plus 3 cations is ascribed to the inert pair effect, which reflects the relatively low energy of the valence s electron pair for atoms of the heavy elements of group 13, 14, and 15. Mercury also exhibits an unexpected behavior. It forms a diatomic ion, made with an HGHG bond. In addition, it is to the expected monatomic ion of mercury, which only has one atom. Transition and intertransition metal elements behave differently than main group elements. Most transition metals cations have plus 2 or plus 3 charges that result from the loss of their outermost s electron first, sometimes followed by the loss of one or two d electrons from the next to outermost shell. For example, iron forms the plus 2 charge by the loss of 4s electrons, and the ion iron 3 by the loss of 4s electrons and one of the 3d electrons. Although the d orbitals of the transition elements are, according to the Aufbau principle, the last to fill when building up electron configurations, the outermost s electrons are the first to be lost when these atoms ionize. When the intertransition metals form ions, They usually have a +3 charge, resulting from the loss of their outermost s electrons and or a d or f electron. Electronic structures of anions. Most monatomic anions form when a neutral nonmetal atom gains enough electrons to completely fill its outer s and p orbitals, thereby reaching the electron configuration of the next noble gas. Thus, it is simple to determine the charge on such a negative ion. The charge is equal to the number of electrons that must be gained to fill the s and p orbitals of the parent atom. Oxygen, for example, has the electron configuration 1s2, 2s2, 2p4, whereas the oxygen anion has the electron configuration of the noble gas neon 1s2, 2s2, 2p6. The two additional electrons required to fill the valence orbitals give the oxide ion the charge of a 2-. 7.2 Covalent bonding. Learning objectives. By the end of this section, you will be able to describe the formation of covalent bonds, define electronegativity, and assess the polarity of covalent bonds. Ionic bonding results from the electrostatic attraction of oppositely charged ions and are typically produced by the transfer of electrons between metallic and nonmetallic atoms. A different type of bonding results from the mutual attraction of atoms for a shared pair of electrons. Such bonds are called covalent bonds. Covalent bonds are formed between two atoms when both have similar tendencies to attract electrons to themselves. For example, two hydrogen atoms bond covalently to form H2 molecule. Each hydrogen atom in the H2 molecule has 2 electrons stabilizing it, giving each atom the same number of valence electrons as the noble gas helium. Compounds that contain covalent bonds exhibit different physical properties than ionic compounds because the attraction between molecules, which are electrically neutral, is weaker than that between electrically charged ions. Covalent compounds generally have much lower melting and boiling points than ionic compounds. In fact, many covalent compounds are liquids or gases at room temperature, and in their states, they are typically much softer than ionic solids. Furthermore, whereas ionic compounds are good conductors of electricity, when dissolved in water, the most covalent compounds are insoluble in water since they are electrically neutral. They are poor conductors of electricity in any state. Formation of covalent bonds. Nonmetal atoms frequently form covalent bonds with other nonmetal atoms. For example, the hydrogen molecule H2 contains a covalent bond between its two hydrogen atoms. Figure 7.4 illustrates why this bond is formed. Starting on the far right, we have two separate hydrogen atoms. Okay. With a particular potential energy indicated by the red line. Along the x-axis is the distance between the two atoms. As the two atoms approach each other, moving left along the x-axis, their valence orbitals 1s begin to overlap. The single electron on each hydrogen atom then interact with both atomic nuclei, occupying the space around both atoms. The strong attraction of each shared electron to both nuclei stabilizes the system, and the potential energy decreases as the bond distance decreases. If the atoms continue to approach each other, the positive changes in the two nuclei begin to repel each other, and the potential energy increases. The bond length is determined by the distance at which the lowest potential energy is achieved. It is essential to remember that energy must be added to break chemical bonds in an endothermic reaction process. Whereas forming chemical bonds releases energy, an exothermic process. In the case of H2, the covalent bond is very strong. A large amount of energy, 436 kilojoules, must be added to break the bonds in 1 mole of hydrogen molecules and cause the atoms to separate. Conversely, the same amount of energy is released when 1 mole of H2 molecules forms from the 2 moles of hydrogen atoms. Pure versus polar covalent bonds. If the atoms that form covalent bonds are identical, as in H2 or Cl2 and other diatomic molecules, then the electrons in the bonds must be shared equally. We refer to this as the pure covalent bond. Electrons shared in pure covalent bonds have an equal probability of being near the nucleus. In the case of Cl2, each atom starts off with 7 valence electrons, and each Cl shares 1 electron with the other, forming a covalent bond. The total number of electrons around each individual atom consists of 6 non-bonding electrons and 2 shared, i.e. bonding electrons, for 8 total electrons, matching the number of valence electrons in the noble gas argon. Since the bonding atoms are identical, Cl2 also features a pure covalent bond. When the atoms linked by a covalent bond are different, the bonding electrons are shared but no longer equally. Instead, the bonding electrons are more attracted to one atom than the other, giving rise to a shift of electron density toward that atom. This unequal distribution of electrons is known as a polar covalent bond, characterized by a partial positive charge on one atom and a partial negative charge on the other. The atom that attracts the electrons more strongly acquires the partial negative charge and vice versa. For example, the electrons in the HCl bond of a hydrogen chloride molecule spend more time near the chlorine atom than near the hydrogen atom. Thus, in an HCl molecule, the chlorine atom carries a partial negative charge and the hydrogen atom has a partial positive charge. Figure 7.5 shows the distribution of electrons in the HCl bond. Note that the shaded area around Cl is much larger than it is around H. Compare this to figure 7.4, which shows that the even distribution of electrons in the H2 nonpolar bond. We sometimes designate the positive and negative atoms in a polar covalent bond using a lowercase Greek letter delta, with a plus sign or a minus sign to indicate whether the atom has a partial positive charge or a partial negative charge. The symbolism is shown for the HCl molecule. Electronegativity. Whether a bond is nonpolar or polar covalent is determined by a property of the bonding atoms called electronegativity. Electronegativity is a measure of the tendency of an atom to attract electrons or electron density toward itself. It determines how the shared electrons are distributed between the two atoms in a bond. The more strongly an atom attracts the electrons in its bonds, the larger its electronegativity. Electrons in a polar covalent bond are shifted toward the more electronegative atom. Thus, the more electronegative atom is the one with the partial negative charge. The greater the difference in electronegativity, the more polarized the electron distribution and the larger the partial charge of the atoms. Figure 7.6 shows the electronegativity value of the elements as proposed by one of the most famous chemists of the 20th century, Linus Pauling. In general, electronegativity increases from left to right across the period to the periodic table and decreases down a group. Thus, the non-essentials, which lie in the upper right, tend to have the highest electronegativities, with fluorine the most electronegative element of all. Metals tend to be less electronegative elements, and the group 1 metals have the lowest electronegativities. Note that noble gases are excluded from this figure because the atoms usually do not share electrons with other atoms since they have full valence shells. While noble gas compounds such as xenon do exist, they can only be formed under extreme conditions, and they do not fit neatly into the general model of electronegativity. Okay, I'm going to pause for a minute. I need to lay down for a minute. All right. Took a short little nap there. I didn't realize how tired I was. So, electronegativity versus electron affinity. We must be careful not to confuse electronegativity and electron affinity. The electron affinity of an element is a measurable physical quantity, namely the energy released and absorbed when an isolated gas phase atom acquires an electron, measured in kilojoules per mole. Electronegativity, on the other hand, describes how tightly an atom attracts electrons in a bond. It is a dimensionless quantity that is calculated, not measured. Pauling derived the first electronegativity values by comparing the amount of energy required to break up different types of bonds. He chose an arbitrary relative scale ranging from 0 to 4. Electronegativity and bond type. The absolute value of the difference in electronegativity of two bonded atoms provides a rough measure of the polarity to be expected in the bond, and thus the bond type. When the difference is very small or 0, the bond is covalent and nonpolar. When it is large, the bond is polar, covalent, or ionic. The absolute values of the electronegativity differences between the atoms and the bonds HH, HCl, and NaCl are 0, 0.9, and 2.1, respectively. The degree to which electrons are shared between atoms varies from completely original to not at all. Figure 7.8 shows a relationship between electronegativity difference and bond type. A rough approximation of the electronegativity differences associated with covalent, polar covalent, and ionic bonds is shown in Figure 7.8. This table is just a general guide, however, with many exceptions. For example, H and F atoms in HF have an electronegativity difference of 1.9, and the NH atoms in NH3 difference of 0.9, yet both of these compounds form bonds that are considered polar covalent. Likewise, the NaCl atoms in NaCl have an electronegativity difference of 2.1, and the Mn and I atoms Mn and Mni2 have a difference of 1, yet both these substances form ionic compounds. The best guide to the covalent or ionic character of a bond is to consider the types of atoms involved and their relative positions in the periodic table. Bonds between two nonmetals are generally covalent. Bonding between a metal and a nonmetal is often ionic. Some compounds contain both covalent and ionic bonds. The atoms in polyatomic ions such as OH, hydroxide, nitrate, and ammonium are held together by polar covalent bonds. However, these polyatomic ions form ionic compounds by combining with ions of opposite charge. For example, potassium nitrate contains sodium and nitrate ions, thus bonding in potassium nitrate is ionic, resulting from the electrostatic attraction between the ions sodium and nitrate, as well as covalent between the nitrogen and oxygen atoms in nitrate. 7.3. Lewis symbols and structures. Write Lewis symbols for neutral atoms and ions. Draw Lewis structures depicting the bonding in simple molecules. Thus far in this chapter, we have discussed the various types of bonds that form between atoms and or ions. In all cases, these bonds involve the sharing or transfer of valence shell electrons between atoms. In this section, we will explore the typical method for depicting valence shell electrons and chemical bonds, namely Lewis symbols and Lewis structures. Lewis symbols. We use Lewis symbols to describe valence electron configurations of atoms and monatomic ions. A Lewis symbol consists of an element symbol surrounded by one dot for each of its valence electrons. And I'll demonstrate how that works the next read through. Lewis structures. We also use Lewis symbols to indicate the formation of covalent bonds, which are shown in Lewis structures. Drawings that describe the bonding in molecules in polyatomic ions. For example, when two chlorine atoms form a chlorine molecule, they share one pair of electrons. And there's the symbol. The Lewis structures indicates that each chlorine atom has 3 pairs of electrons that are not used in bonding, called lone pairs, and one shared pair of electrons written between the atoms. A dash or line is sometimes used to indicate a shared pair of electrons. A single shared pair of electrons is called a single bond. Each chlorine atom interacts with 8 valence electrons, the 6 in the lone pairs and 2 in the single bond. The octet rule. The other halogen molecules form bonds like those in the chlorine molecule, 1 single bond between atoms and 3 lone pairs of electrons per atom. This allows each halogen atom to have noble gas electron configuration. The tendency of main group atoms to form enough bonds to attain 8 valence electrons is known as the octet rule. The number of bonds that an atom can form can be predicted from the number of electrons needed to reach an octet. This is especially true in the nonmetals of the second period of the periodic table. For example, each atom of group 14 element has 4 electrons in its outermost shell and therefore requires 4 more electrons to reach an octet. These 4 electrons can be gained by forming 4 covalent bonds, as illustrated here for carbon in CCl4. And carbon tetrachloride, and silicon in silane. Because hydrogen only needs 2 electrons to fill its valence shell, it is an exception to the octet rule. The transition elements and inner transition elements do not follow the octet rule. Group 15 elements such as nitrogen have 5 valence electrons in the atomic Lewis symbol, 1 lone pair and 3 unpaired electrons. To obtain an octet, these atoms form 3 covalent bonds, as in NaH ammonia. Oxygen and other atoms in group 16 obtain an octet by forming 2 covalent bonds, double and triple bonds. As previously mentioned, when a pair of atoms shares 1 pair of electrons, we call this a single bond. However, a pair of atoms may need to share more than 1 pair of electrons in order to achieve the requisite octet. A double bond forms when 2 pairs of electrons are shared between a pair of atoms, as between the carbon and oxygen atoms as formaldehyde, and between 2 carbon atoms in ethylene. A triple bond forms when 3 electron pairs are shared by a pair of atoms, as in carbon monoxide and cyanide ion. Writing Lewis structures with the octet rule. For very simple molecules and molecular ions, we can write the Lewis structures by merely pairing up the unpaired electrons on the constituent atoms. Here's the examples. For more complicated molecules and molecular ions, it is helpful to follow the step-by-step procedure outlined here. 1. Determine the total number of valence outer shell electrons. For cations, subtract 1 electron for each positive charge. For anions, add 1 electron for each negative charge. Draw a skeleton structure for the molecular ion, arranging the atoms around a central atom. Generally, at least electronegative element should be placed in the center. Connect each atom to the central atom with a single bond. Distribute the remaining electrons as lone pairs of the terminal atoms, completing an octet around each atom. Place all remaining electrons on the central atom. Rearrange the electrons of the outer atoms to make multiple bonds with the central atom in order to obtain octets wherever possible. Let us determine the Lewis structures for silane. That is the formate ion. NO plus would be what, like nitroxonium? I don't know. And OF2. Oh, sorry. Nope. NO plus would be like nitrogen monoxide ion. And OF2 would be oxygen difluoride. 1. I forget. Determine the total number of valence. Oh, you're just going to show us how. So I was just going to go through. I'm not going to read any of that. It's just an example. That's not part of an example. Exceptions to the octet rule. Many covalent molecules have central atoms that do not have 8 electrons in their Lewis structures. These molecules fall into 3 categories. Odd electron molecules have an odd number of valence electrons and therefore have an unpaired electron. Electron-deficient molecules have a central atom that has fewer electrons than needed for a noble gas configuration. Hypervalent molecules have a central atom that has more electrons than needed for a noble gas configuration. Odd electron molecules. We call molecules that contain odd number of electrons free radicals. Nitric oxide, NO, is an example of an odd electron molecule. It is produced in an internal combustion engines when oxygen and nitrogen react at high temperatures. To draw the Lewis structure for an odd electron molecule like NO, we follow the same 5 steps we would for other molecules, but with minor changes. 1. Determine the total number of valence electrons. The sum of the valence electrons is 5 from N and 6 from O, which gives you 11. The odd number immediately tells us we have a free radical, so we know that not every atom can have 8 electrons in its valence shell. Draw a skeleton structure of the molecule. We can easily draw a skeleton with an NO single bond. Distribute the remaining electrons as lone pairs on the terminal atoms. In this case, there's no central atom. So we distribute the electrons around both atoms. We give 8 electrons to the more electronegative atom in these situations. Thus, oxygen has a filled valence shell. Place all remaining electrons on the central atom. Since there are no remaining electrons, the step does not apply. Rearrange the electrons to make multiple bonds with the central atom in order to obtain octets wherever possible. We know that odd electron molecule cannot have an octet for every atom, but we want to get each atom to as close to an octet as possible. In this case, nitrogen has only 5 electrons around it. To move closer to an octet for nitrogen, we take one of the lone pairs from oxygen and use it to form an NO double bond. We cannot take another lone pair of electrons on oxygen to form a triple bond because nitrogen would then have 9 electrons. Hold on one sec. Oh, there it is. Okay. I'm going to put my sweats on real quick. Getting a little chilly. Dang it. Sorry. Tried moving my chair back and it moved back 0 inches. I have to take a shower soon. Cold shower. Give me that caffeine-like feel. Blah, 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 blah. Electron-deficient molecules. We will also encounter a few molecules that contain central atoms that do not have a filled valence shell. Generally, these are molecules with central atoms from groups 2 and 13, outer atoms that are hydrogen or other atoms that do not form multiple bonds. For example, in the Lewis structure of beryllium dihydride, BeH2, and boron trifluoride, the beryllium and boron atoms each have only 4 and 6 electrons respectively. It is possible to draw the structure with a double bond between a boron atom and a fluorine atom in BF3, satisfying the octet rule, but experimental evidence indicates the bond lengths are closer to that expected for BF single bonds. This suggests that the best Lewis structure has 3 BF single bonds and an electron-deficient boron. The reactivity of the compound is also consistent with an electron-deficient boron. However, the BF bonds are slightly shorter than what is actually expected for BF single bonds, indicating that some double bond character is found in the actual molecule. An atom like the boron atom in BF3, which does not have 8 electrons, is very reactive. It readily combines with a molecule containing an atom with a lone pair of electrons. For example, ammonium reacts with boron trifluoride because the lone pair on nitrogen can be shared with the boron atom. Hypervalent molecules. Elements in the second period of the periodic table can accommodate only 8 electrons in their valence shell orbitals because they only have 4 valence orbitals. Elements in third and higher periods have more than 4 valence orbitals that can share more than 4 pairs of electrons with other atoms because they have empty d orbitals in the same shell. Molecules formed from these elements are sometimes called hypervalent molecules. Figure 712 shows the Lewis structures for 2 hypervalent molecules, phosphorus pentachloride and sulfur hexafluoride. In some hypervalent molecules, such as iodine pentafluoride, and xenon tetrafluoride, some of the electrons in the outer shell of the central atom are lone pairs. When we write the Lewis structures for these molecules, we find that we have electrons left over after filling the valence shells of the outer atoms with 8 electrons. These additional electrons must be assigned to the central atom. 7.4. Formal charges and resonance. By the end of this section, you'll be able to compute formal charges for atoms in any Lewis structure, use formal charges to identify the most reasonable Lewis structure for a given molecule, explain the concept of resonance, and draw Lewis structures representing resonance forms for a given molecule. In the previous section, we discussed how to write Lewis structures for molecules and polyatomic ions. As we have seen, however, in some cases, there is seemingly more than one valid structure for a molecule. We can use the concept of formal charges to help us predict the most appropriate Lewis structure when more than one is reasonable. Calculating formal charge. The formal charge of an atom in a molecule is the hypothetical charge of the atom, or the atom would have if we could redistribute the electrons in the bonds evenly between the atoms. Another way of saying this is that the formal charge results when we take the number of valence electrons of a neutral atom, subtracting the non-bonding electrons, and then subtract the number of bonds connected to that atom in the Lewis structure. Thus, we calculate formal charge as follows. And then there's the formal charge rule. We can double-check formal charge calculations by determining the sum of the formal charges for the whole structure. The sum of the formal charges of all the atoms in a molecule must be 0. The sum of formal charges in an ion should equal the charge of the ion. We must remember that the formal charge calculated for an atom is not the actual charge of the atom in the molecule. Formal charge is only a useful bookkeeping procedure. It does not indicate the presence of actual charges. Using formal charge to predict molecular structure. The arrangement of atoms in a molecule or ion is called its molecular structure. In many cases, following the steps for writing Lewis structures may lead to more than one possible molecular structure. Different multiple bond and lone pair electron placements or different arrangements of atoms, for instance. For a few guidelines involving formal charge can be helpful in deciding which of the possible structures is most likely for a particular molecule or ion. 1. A molecular structure in which all formal charges are zero is preferable to one in which some formal charges are not zero. 2. If the Lewis structure must have non-zero formal charges, the arrangement with the smallest non-zero formal charges is preferable. Lewis structures are preferable when adjacent formal charges are zero or of the opposite sign. When we must choose among several Lewis structures with similar distributions of formal charges, the structure with the negative formal charges on the more electronegative atoms is preferable. To see how these guidelines apply, let us consider some possible structures for carbon dioxide. We know from our previous discussion that less electronegative atom typically occupies the central position, but formal charges allow us to understand why this occurs. We can draw three possibilities for the structure: carbon in the center and double bonds, carbon in the center with a single and triple bond, and oxygen in the center with double bonds. Comparing the three formal charges, we can definitively identify the structure on the left as being preferable because it has only formal charges of zero. As another example, the thiocyanate ion, an ion formed from a carbon atom, a nitrogen atom, and a sulfur atom, could have three different molecular structures: NCS, CNS, or CSN. The formal charges present in each of these molecular structures can help us pick the most likely arrangement of atoms. Possible Lewis structures and the formal charges for each of the three possible structures for the thiocyanate ion are shown here. I think I know what I want to do for a project for this. I think a good project would be to develop, so the issue is when I went through all of this stuff, there was we look at things as if they're stationary or not moving, as if they're individual objects. So like one of these NCS, CNS, one of these ions is just whatever the structure is. It's just it's it. But if it's you're only looking at that structure, you're not considering everything around it. So you also have multiple bodies that are going to influence that single body in that environment, in the environment. So I wonder if there's like a way to create a database or like it's just a spreadsheet that would contain all the possible arrangements of the atoms, and then go look up all the data for all the ones that do exist, maybe, and then try to figure out why. I don't know. That sounds kind of fun. Note that the sum of the formal charges in each case is equal to the charge of the ion. However, the first arrangement of atoms is preferred because it has the lowest number of atoms with non-zero formal charges. Also, it places the least electronegative atom in the center and the negative charge on the more electronegative element. Resonance. Notice that the more likely structure for the nitrite anion in 7.8 may actually be drawn in two different ways, distinguished by the locations of the NO and N-double-O bonds. If nitrite ions do indeed contain a single and double bond, we would expect for the two bond lengths to be different. A double bond between two atoms is shorter and stronger than a single bond between the same two atoms. Experiments show, however, that both NO bonds and NO2 have the same length, same strength and length, and are identical in all other properties. It is not possible to write a single Lewis structure for NO2 in which nitrogen has an octet and both bonds are equivalent. Instead, we use the concept of resonance. If two or more Lewis structures with the same arrangement of atoms can be written for a molecular ion, the actual distribution of electrons is an average of that shown by the various Lewis structures. The actual distribution of electrons in each of the nitrogen-oxygen bonds is in NO2 is the average of a double bond and a single bond. We call the individual Lewis structures resonance forms. The actual electronic structure of the molecule is called a resonance hybrid of the individual resonance forms. A double-headed arrow between Lewis structures indicates that they are resonance forms. We should remember that a molecule described as a resonance hybrid never possesses an electronic structure described by either resonance form. It does not fluctuate between resonance forms. Rather, the actual electronic structure is always the average of that shown by the resonance forms. George Wieland, one of the pioneers of resonance theory, used a historical analogy to describe the relationship between resonance forms and resonance hybrids. A medieval traveler, having never seen a rhinoceros, described it as a hybrid of a dragon and a unicorn because it had many properties in common with both. Just as a rhinoceros is neither a dragon sometimes nor a unicorn at other times, a resonance hybrid is neither of its resonance forms at any given time. Like a rhinoceros, it is a real entity that experimental evidence has shown to exist. It has some characteristics in common with its resonance forms, but the resonance forms themselves are convenient, imaginary images. The carbonate anion provides a second example of resonance. One oxygen atom must have a double bond to carbon to complete the octet of the central atom. All oxygen atoms, however, are equivalent, and the double bond could form from any one of the three atoms. This gives rise to three resonance structures of the carbonate ion, because we can write three identical resonance structures. We know that the actual arrangement of the electrons in the carbonate ion is the average of the three structures. Again, experiments show that all three CO bonds are exactly the same. 7.5. Strengths of ionic and covalent bonds. By the end of this section, you'll be able to describe the energetics of covalent and ionic bond formation and breakage. Oh my gosh, I'm sorry. I don't know why I'm having such a hard time pronouncing simple words. Use the Born-Haber cycle to compute lattice energies for ionic compounds. Use average covalent bond energies to estimate enthalpies of reaction. I don't know why that's so frustrating, but it's just like, come on, man. A bond strength describes how strongly each atom is joined to another atom, and therefore how much energy is required to break the bond between the two atoms. In this section, you will learn about the bond strength of covalent bonds, and then compare that to the strength of ionic bonds, which is related to the lattice energy of a compound. Bond strength, covalent bonds. Stable molecules exist because covalent bonds hold the atoms together. We measure the strength of a covalent bond by the energy required to break it, that is, the energy necessary to separate the bonded atoms. Separating any pair of bonded atoms requires energy. The stronger a bond, the greater the energy required to break it. The energy required to break a specific covalent bond in 1 mole of gaseous molecules is called the bond energy, or the bond dissociation energy. The bond energy for a diatomic molecule is defined as the standard enthalpy change for the endothermic reaction. There's the reaction. For example, the bond energy of the pure covalent hydrogen-hydrogen bond is 436 kilojoules per mole of hydrogen-hydrogen bonds broken. Molecules with 3 or more atoms have 2 or more bonds. The sum of all bond energies in such a molecule is equal to the standard enthalpy change for the endothermic reaction that breaks all the bonds in the molecule. For example, the sum of the 4 CH bond energies in methane, 1,660 kilojoules, is equal to the standard enthalpy change of the reaction. There it is. The average carbon-hydrogen bond energy is 1660 divided by 4 equals 415 kilojoules per mole, because there are 4 moles of CH bonds broken per mole of reaction. Although the 4 CH bonds are equivalent in the original molecule, they do not each require the same energy to break. Once the first bond is broken, the remaining bonds are easier to break. The 415 kilojoules per mole value is the average, not the exact value required to break any one bond. The strength of a bond between 2 atoms increases as the number of electron pairs in the bond increases. Generally, as the bond strength increases, the bond length decreases. Thus, we find that triple bonds are stronger and shorter than double bonds between the same 2 atoms. Likewise, double bonds are stronger and shorter than single bonds between the same 2 atoms. Average bond energies for some common bonds appear in Table 7.2. and a comparison of bond lengths and bond strengths for some common bonds appears in Table 7.3. When one atom bonds to various atoms in a group, the bond strength typically decreases as we move down the group. For example, carbon fluorine is 439, carbon chlorine is 330, carbon bromine is 275, so on. We can use bond energies to calculate approximate enthalpy changes for reactions where enthalpies of formation are not available. Calculations of this type will also tell us whether a reaction is exothermic or endothermic. An exothermic reaction results when the bonds in the products are stronger than the bonds in the reactants. An endothermic reaction results when the bonds in the products are weaker than those in the reactants. The enthalpy change, delta H, for a chemical reaction is approximately equal to the sum of the energy required to break all bonds of the reactants, plus the energy released when all the bonds are formed in the products. This can be expressed mathematically in the following way. In the expression, the symbol sigma means the sum of, and D represents the bond energy in kilojoules per mole, which is always a positive number. The bond energy obtained from a table will depend on whether the particular bond in a single, double, or triple bond. Thus, in calculating enthalpies in this manner, it is important that we consider the bonding in all reactants and products. Because D values are typically averages for one type of bond in many different molecules, this calculation provides a rough estimate, not an exact value for the enthalpy of reaction. Consider the following reaction. There it is. To form 2 moles of HCl, 1 mole of HH bonds, and 1 mole of ClCl bonds must be broken. The energy required to break these bonds is the sum of the bond energy of the hydrogen-hydrogen bond and the chlorine-chlorine bond. During the reaction, 2 moles of hydrogen and chlorine bonds are formed, releasing 2 times 432 kilojoules or 864 kilojoules. Because the bonds in the products are stronger than those in the reactants, the reaction releases more energy than it consumes. This excess energy is released as heat, so the reaction is exothermic. Appendix G gives a value for the standard molar enthalpy of formation of HCl. Delta H formation of negative 92.307 kilojoules per mole. Twice that value is negative 184.6 kilojoules, which agrees well with the answer obtained earlier for the formation of the 2 moles of HCl. Ionic bond strength and lattice energy. An ionic compound is stable because of the electrostatic attraction between its positive and negative ions. The lattice energy of a compound is a measure of the strength of this attraction. The lattice energy, delta H lattice, of an ionic compound is defined as the energy required to separate 1 mole of the solid into its component gaseous ions. For the ionic solid, Mx, the lattice energy is the enthalpy change of the process. Note that we are using the convention where the ionic solid is separated into ions, so our lattice energies will be endothermic. Some texts use the equivalent but opposite convention, defining lattice energy as the energy released when separate ions combine to form a lattice and giving negative values. Thus, if you are looking up lattice energies in another reference, be certain to check which definition is being used. In both cases, a larger magnitude for lattice energy indicates a more stable ionic compound. For sodium chloride, delta H lattice is 769 kilojoules. Thus, it requires 769 kilojoules to separate 1 mole of sodium solid chloride into gaseous sodium and chloride ions. When 1 mole of each of gaseous sodium and chloride ions forms solid sodium chloride, 769 kilojoules of heat is released. The lattice energy, delta H lattice, of an ionic crystal can be expressed by the following equation derived from Coulomb's law governing the forces between electric charge. Delta H lattice equals that equation, in which C is a constant that depends on the type of crystal structure. C plus and Z minus are the charges on the ions, and R0 is the interionic distance, the sum of the radii of the positive and negative ions. Thus, the lattice energy of an ionic crystal increases rapidly as the charges of the ions increase and the sizes of the ions decrease. When all other parameters are kept constant, doubling the charge of both the cation and anion quadruples the lattice energy. For example, the lattice energy of lithium fluoride is 1,023 kilojoules per mole, whereas magnesium oxide is 3,900 kilojoules per mole. Different interatomic distances produce different lattice energies. For example, we can compare the lattice energy of magnesium fluoride to that of magnesium iodide. to observe the effect on lattice energy of the smaller size of the fluoride ion as compared to iodide. The Born-Haber cycle. It is not possible to measure lattice energies directly. However, the lattice energy can be calculated using the equation given in the previous section or by using a thermochemical cycle. The Born-Haber cycle is an application of Hess's law that breaks down the formation of an ionic solid into a series of individual steps. The delta H of formation, the ionic ionization energy, electron affinity, the delta H of sublimation, D is the dissociation energy, and delta H lattice. Okay, we begin with the elements in their most common states, cesium, fluoride. Hold on, is that an example? I was just explaining this guy. Not going to read it. It's an example. No, I'll read it because it shows. So basically what they do is they arrange the different equations that you could get from these features, and you get, basically, you do these different reactions together. You add up all of the different, so you got, here's one reaction. This is the sublimation, ionization energy, half of D, electron affinity, half of delta H lattice, and then you form it, given its elemental, starting from the elements. All right. You begin with the elements in their most common states, cesium and fluorine. Delta HS represents the conversion of solid cesium into gas, and then the ionization energy converts the gaseous cesium atoms into cations. In the next step, we account for the energy required to break the fluorine-fluorine bond to produce fluorine atoms. Converting 1 mole of fluorine atoms into fluoride ions is an exothermic process. So this step gives off energy. And this shown as decreasing along the y-axis. We now have 1 mole of CS cations and 1 mole of F anions. These ions combine to produce solid cesium fluoride. The enthalpy change in this step is the negative of the lattice energy, so it is also an exothermic quantity. The total energy involved in this conversion is equal to the experimentally determined enthalpy of formation, delta HF, of the compound from its elements. In this case, the overall change is exothermic. Hess's law can be used to show the relationship between the enthalpies of the individual steps and the enthalpy of formation. Table 7.4 shows it. Thus, the lattice energy can be calculated from other values. For cesium fluoride, using this data, the lattice energy is that. The Born-Haber cycle may also be used to calculate one of the other quantities in the equation for lattice energy, provided that the remainder is known. For example, if the relevant enthalpy of sublimation, delta HS, ionization energy, bond dissociation enthalpy, lattice energy, and then standard enthalpy of formation are known, the Born-Haber cycle can be used to determine the electron affinity of an atom. Lattice energies calculated for ionic compounds are typically much higher than bond dissociation energies measured for covalent bonds. Whereas lattice energies typically fall in the range of 600 to 4,000 kilojoules per mole, covalent bond dissociation energies are typically between 150 to 400 kilojoules per mole for single bonds. Keep in mind, however, that these are not directly comparable values. For ionic compounds, lattice energies are associated with many interactions as cations and anions packed together in an extended lattice. For covalent bonds, the molecular dissociation energy is associated with the interaction of just 2 atoms. Seven 6, molecular structure and polarity. Learning objectives. By the end of this section, you'll be able to predict the structures of small molecules using valence shell electron pair repulsion theory, VSEPR. Explain the concepts of polar covalent bonds and molecular polarity. Assess the polarity of a molecule based on its bonding and structure. Thus far, we have used 2-dimensional Lewis structures to represent molecules. However, molecular structure is actually 3-dimensional, and it is important to be able to describe molecular bonds in terms of their distances, angles, and relative arrangements in space. A bond angle is the angle between any 2 bonds that include a common atom, usually measured in degrees. A bond distance, or bond length, is the distance between the nuclei of 2 bonded atoms along the straight line joining the nuclei. Bond distances are measured in angstroms, or picometers. VSEPR theory, valence shell electron pair repulsion theory, enables us to predict the molecular structure, including approximate bond angles around a central atom of a molecule from an examination of the number of bonds and electron pairs in its Lewis structure. The VSEPR model assumes that electron pairs in the valence shell of a central atom will adopt an arrangement that minimizes repulsions between these electron pairs by maximizing the distance between them. The electrons in the valence shell of a central atom form either bonding pairs of electrons located primarily between bonded atoms or lone pairs. The electrostatic repulsion of these electrons is reduced when the various regions of high electron density assume positions as far from each other as possible. VSEPR theory predicts the arrangement of electron pairs around each central atom and, usually, the correct arrangement of atoms in a molecule. We should understand, however, that the theory only considers electron pair repulsions. Other interactions, such as nuclear-nuclear repulsions and nuclear electron attractions, are also involved in the final arrangement that atoms adopt in a particular molecular structure. As a simple example of VSEPR theory, let us predict the structure of a gaseous BeF2 molecule. The Lewis structure of beryllium difluoride, or maybe it's just beryllium fluoride, shows only two electron pairs around the central beryllium atom, with two bonds and no lone pair electrons on the central atom. The bonds are as far apart as possible, and the electrostatic repulsion between these regions of high electron density is reduced to a minimum when they are on opposite sides of the central atom. The bond angle is 180 degrees. Figure 716 illustrates this and other electron pair geometries that minimize the repulsions among regions of high electron density. Let's see. Two regions of electron density around a central atom in a molecule form a linear geometry. 3 form a trigonal planar geometry. 4 form a tetrahedral geometry. 5 form a trigonal bipyramidal geometry. And 6 form an octahedral geometry. Boop, boop, boop. We differentiate between these two situations by naming the geometry that includes all electron pairs, the electron pair geometry. The structure that includes only the placement of atoms in the molecule is called the molecular structure. The electron pair geometries will be the same as the molecular structure when there are no lone electrons around the central atom, but they will be different when there are lone pairs present on the central atom. For example, the methane molecule CH4, which is the major component of natural gas, has 4 bonding pairs of electrons around the central carbon atom. The electron pair geometry is tetrahedral, as is the molecular structure. On the other hand, the ammonium molecule, NH3, also has the 4 electron pairs associated with the nitrogen atom, and thus is a tetrahedral electron pair geometry. One of these regions, however, is a lone pair that is not included in the molecular structure, and this lone pair influences the shape of the molecule. As seen in 718, small distortions from the ideal angles in figure 716 can result from differences in repulsion between various regions of electron density. VSEPR theory predicts these distortions by establishing an order of repulsions and an order of the amount of space occupied by different kinds of electron pairs. The order of electron pair repulsions from greatest to least repulsion is that this order of repulsion determines the amount of space occupied by different regions of electrons. A lone pair of electrons occupies a larger region of space than the electrons in a triple bond. In turn, electrons in a triple bond occupy more space than those in a double bond, and so on. The order of sizes from the largest to smallest is lone pair, triple bond, double bond, single bond. Consider formaldehyde, H2CO, which is used as a preservative for biological and anatomical specimens. This molecule has regions of high electron density that consist of 2 single bonds and 1 double bond. The basic geometry is trigonal planar with 120-degree bond angles, but we see that the double bond causes slightly larger angles, and the angle between the single bonds is slightly smaller. In the ammonia molecule, the 3 hydrogen atoms attached to the central nitrogen are not arranged in a flat trigonal planar molecular structure, but rather in a 3-dimensional trigonal pyramid, with the nitrogen atom at the apex of the 3 hydrogen atoms forming the base. The ideal bond angles in a trigonal pyramid are based on the tetrahedral electron pair geometry. Again, there are slight deviations from the ideal because lone pairs occupy larger regions of space than do bonding electrons. The HNH bonding angles in NH3 are slightly smaller than 109.5 degrees angle on a regular tetrahedron because the lone pair bonding pair repulsion is greater than the bonding pair repulsion. Figure 719 illustrates the ideal molecular structures which are predicted based on the electron pair geometries for various combinations in lone pairs and bonding pairs. According to Vesper theory, the terminal atom locations are equivalent within the linear, trigonal, planar, and tetrahedral electron pair geometries, the first three rows of the table. It does not matter which X is placed with a lone pair because the molecules can be rotated to convert positions. For trigonal bipyramidal electron pair geometries, however, there are two distinct X positions, as shown in Figure 720, an axial position and an equatorial position. As shown in Figure 719, the axial position is surrounded by bond angles of 90 degrees, whereas the equatorial position has more space available because of the 120-degree bond angles. In a trigonal bipyramidal electron pair geometry, lone pairs always occupy equatorial positions because these more spacious positions can more easily accommodate the larger lone pairs. Theoretically, we can come up with three possible arrangements for the three bonds and two lone pairs for the chlorine trifluoride molecule. The stable structure is the one that puts the lone pairs in the equatorial locations, giving T-shaped molecular structure. Okay. Excuse me. When a central atom has two lone electron pairs and four bonding regions, we have an octahedral electron pair geometry. The two lone pairs are on opposite sides of the octahedron, giving a square planar molecular structure that minimizes lone pair repulsions. Predicting electron pair geometry and molecular structure. The following procedure uses Vesper theory to determine the electron pair geometries and a molecular structure. 1. Write the Lewis structure of the molecule or polyatomic ion. 2. Count the number of regions of electron density around the central atom. A single, double, or triple bond counts as one region of the electron density. 3. Identify the electron pair geometry based on the number of regions of electron density, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, or octahedral. Use the number of lone pairs to determine the molecular structure. If more than one arrangement of lone pairs and chemical bonds is possible, choose the one that will minimize repulsions, remembering that lone pairs occupy more space than multiple bonds, which occupy more space than single bonds. In trigonal bipyramidal arrangements, repulsion is minimized when every lone pair is in an equatorial position. In an octahedral arrangement with two lone pairs, repulsion is minimized when the lone pairs are on opposite sides of the central atom. The following examples illustrate the use of Vesper theory to predict the molecular structure of molecules or ions that have no lone pairs of electrons. In this case, the molecular structure is identical to the electron pair geometry. Okay. Molecular structure for multicenter molecules. When a molecular polyatomic ion has only one central atom, the molecular structure completely describes the shape of the molecule. Larger molecules do not have a single central atom, but are connected by a chain of interior atoms that each possess a local geometry. The way these local structures are oriented with respect to each other also influences the molecular shape, but such considerations are largely beyond the scope of this introductory discussion. For our purposes, we will only discuss on determining the local structures. Molecular polarity and dipole moment. As discussed previously, polar covalent bonds connect two atoms with differing electronegativities, leaving one atom with a partial positive charge and the other atom with a partial negative charge, as the electrons are pulled toward the more electronegative atom. This separation of charge gives rise to a bond dipole moment. The magnitude of a bond dipole moment is represented by the Greek letter mu and is given by the formula shown here, where the distance is the magnitude of the partial charges. And the r is the distance between the charges, so mu equals qr. This bond's moment can be represented as a vector, a quantity having both direction and magnitude. Dipole vectors are shown as arrows pointing along the bonds from a less electronegative atom toward the more electronegative atom. A small plus sign is drawn on the less electronegative atom to indicate the partially positive end of the bond. The length of the arrow is proportional to the magnitude of the electronegativity difference between the two atoms. A whole molecule may also have a separation of charge depending on its molecular structure and the polarity of each of its bonds. If such a charge separation exists, the molecule is said to be a polar molecule. Otherwise, the molecule is said to be nonpolar. The dipole moment measures the extent of net charge separation in the molecule as a whole. We determine the dipole moment by adding the bond moments in three-dimensional space, taking into account the molecular structure. For diatomic molecules, there is only one bond, so its bond dipole moment determines the molecular polarity. Sorry, one sec. So their dipole moment is 0. For heteronuclear molecules such as CO, there's a small dipole moment. For HF, there is a larger dipole moment because there is a larger difference in electronegativity. When a molecule contains more than one bond, the geometry must be taken into account. If the bonds in a molecule are arranged such that their bond moments cancel, then the molecule is nonpolar. This is the situation in CO2. Each of the bonds is polar, but the molecule as a whole is nonpolar. From the Lewis structure and using VSEPR theory, we determined that CO2 molecule is linear with polar CO double O bonds on opposite sides of the carbon atom. The bond moments cancel because they are pointed in opposite directions. In the case of the water molecule, the Lewis structure again shows that there are two bonds to a central atom, and the electronegativity difference again shows that each of these bonds is a non-zero bond moment. In this case, however, the molecular structure is bent because of the lone pairs on O. And the two bond moments do not cancel. Therefore, water does have a net dipole moment and is a polar molecule. The OCS molecule has a structure similar to carbon dioxide, but a sulfur atom has replaced one of the oxygen atoms. To determine if this molecule is polar, we draw the molecular structure. VSEPR theory predicts a linear molecule. The CO bond is considerably polar, although C and S have very similar electronegativity values. S is slightly more electronegative than C, and so the CS bond is slightly polar. Because oxygen is more electronegative than sulfur, the oxygen end of the molecule is the negative end. Chloromethane is a tetrahedral molecule with three slightly polar CH bonds and a more polar CCl bond. The relative electronegativities of the bonded atoms H, C, and L, and so that the bond moments all point toward the Cl at the end of the molecule, and sum to yield the considerable dipole moment. For molecules of high symmetry, such as boron trifluoride, methane, phosphorus pentafluoride, and sulfur hexafluoride, all the bonds are of identical polarity, and they are oriented in the geometries that yield nonpolar molecules. Molecules of less geometric symmetry, however, may be polar even when all bond moments are identical. For these molecules, the direction of the equal bond moments are such that they sum to give a non-zero dipole moment and a polar molecule. Examples of such molecules include hydrogen sulfide and ammonia. To summarize, to be polar, a molecule must contain at least one polar covalent bond, have a molecular structure such that the sum of the vectors of each bond dipole moment does not cancel. Properties of polar molecules. Polar molecules tend to align when placed in an electric field with the positive end of the molecule oriented toward the negative plate and the negative end toward the positive plate. We can use an electrically charged object to attract polar molecules, but nonpolar molecules are not attracted. Also, polar solvents are better at dissolving polar substances, and nonpolar solvents are better at dissolving nonpolar substances. And that's it.